This is our last section for this chapter, and in this section, we're going to define complex numbers. We start by solving x squared equal to -1 by square rooting both sides. Don't forget to put the plus or minus for your two unique solutions. The result is the square root of -1, which up until now we replace with a statement like, no real solutions. In order for us to talk about and define these non-real numbers, we must look beyond the set of real numbers. The complex number system is a set that's bigger than that of the real numbers, one that includes the soon-to-be-defined square root of a negative number. We define the square root of -1 to be I, where I, by definition, squared equals -1. Going back to the first slide, we now have a replacement for the square root of -1. In simplifying, we simplify as usual, now with the added step of replacing the negative under the radical with I. So the square root of 36 is 6, and the square root of the -1 we replace with I. The negative in front of the radical here just means that our final result will be negative. The negative under the radical says that we're going to end up with an imaginary result. We simplify the square root of 50 by the method we talked about early in this chapter. We have to be careful when we are multiplying or dividing radical factors, since only real radical factors can be multiplied or divided. What this means is that you must replace the negative under the radical with I before you begin multiplying the radical factors together. So as you can see here, replacing the negative under the radical with I as our first step. Very, very necessary step. After doing so, the radical 3's are real and therefore can be combined. The I squared gives us -1, and the square roots of 3 simplify for 3. Here we start the same way by replacing the square root of -1 with I. After that, we can multiply the square root of 2 and 8. And this gives us the square root of 16, which gives us 4, for a final result of 4i. With division, we still need to replace the square root of -1 with I. And after doing so, we'll apply the quotient rule for radicals, the square root of 27 over 3, which gives us the square root of 9, in the end 3i. Next, we move on to subtraction of complex numbers. And we're going to add the real parts, we'll add the imaginary parts. Start by distributing the negative to free up all of the terms. And after doing so, the problem is a matter of adding like terms. Now we have multiplication of binomial factors. Notice how these binomials are conjugates of one another. And because of this, just like we saw earlier in this chapter, the radicals should multiply away. We will also see that I, since it's the square root of -1, and represents a radical factor, will multiply away as well. So we FOIL as usual, multiplying it all out. We need the fact that I squared is -1, and completely simplifying, we get 30 in the end. For this problem, we are essentially needing to remove the I in the denominator. Recall, we don't leave radicals in the denominator. You are expected to remove those radicals from the denominator as discussed earlier in this chapter. We only have a problem with I and not with 7. And you know that if you multiply I by I, you get I squared, which represents -1. Keep in mind that what you do to the denominator, you must also do to the numerator. So therefore, we're just multiplying by the same. It represents the same value. For our last example, we have a case where the denominator is a binomial. It will always take a binomial, and specifically its conjugate, to remove I from the denominator. The conjugate of 3 minus I is 3 plus I, and again, what you do to the denominator, you must do to the numerator. We have quite a bit of work to do to simplify, and what you find is that the denominator is going to be easy to multiply out, since you're dealing with a binomial multiplied by its conjugate. It's always the numerator that will require the most amount of work. So in the numerator, we FOIL to multiply. Replacing the simplified numerator over that denominator, we finish by getting this expression in the a plus bi form. And this requires us then to separate the terms out. Presently, we have the numerator over a common denominator. After doing so, we reduce each term. Thank you.